covering the low-pass filter op-amp circuit, and that's the schematic of the basic. We take the negative feedback. We take a parallel combination of capacitor and a resistor, and then we put a resistor in series with it. Connect that to our source, which forms a low-pass filter. Now, this is an active low-pass filter. This version here, this is a passive low-pass filter. It's passive because there's no power supply. At least there's no DC power supply connected to it. And the frequency response of this filter is omega 0 is 1 over RC, is time constant. And then you can calculate the gain of this circuit. Some algebra. This is the gain of the circuit here. And then we can calculate the phase shift through the circuit also. So this version of the circuit right here, designing this filter, you want to basically calculate the two resistors and a capacitor. So if the feedback resistor RF is the same as the R series source resistor, basically, the circuit behaves just like the previous circuit here. It behaves very similar to it. So if we mathematically solve for this function going back here, we end up with a formula. The alpha with these classes equals to this, and we're assuming an ideal op-amp here, so we don't have to include the actual gain of the op-amp. So this RF over RS, this is the gain of the low-pass filter, and then the time constant of cutoff is equal to RF minus C sub F. And again, we keep this in the S domain. We're basically putting, we're not looking at exact frequencies yet. So to design a low-pass filter, the term RF over RS is the DC gain of the circuit. And unless it's specified differently, you can set RF equal to R sub S. And for example, in a homework assignment for this low-pass filter, you can design a op-amp low-pass filter, and says the amplitude is 3.2 volts. The frequency is the last four numerical digits of the Z number in hertz, and then there's a noise amplitude, a noise signal with 2 volt amplitude, and a 30 kilohertz frequency. So it doesn't say that the circuit is required to have gain in the specification here. So keeping that in mind, that basically would say that your version, you might take RF equal to R sub S, just to simplify the circuit sum. So this is probably the first hint for that problem, to make those two resistors the same. And the reasoning of that is that the low-pass filter is supposed to stop high-frequency interfering signals or noise, and adding gain to that circuit is really just going to escalate the noise issue with it. So you can probably just set the gain equal to 1. It's actually a minus 1 because of the inversion. So a designer for a low-pass filter. So that's pretty much it in terms of the equations. This equation here. So we go and design a filter, and this is let's say this is our piece-wise input here. It's two sinusoidal inputs to the circuit. One is it's in trigger trigonometric form. One is 5 sine 2 pi f1t, and the other is 5 sine 2 pi f2t. So the question is, we want to design a low-pass filter that will pass this frequency and it will reject the second frequency. So with that in mind, we can give some frequencies to the F1 and F2, and we know both of these have the same amplitude, which is 5 volts, and we'll assume the first signal F1 is a 100 hertz, and it's a musical tone. The second frequency F2, we'll say is an unwanted noise frequency, and it's 30 kilohertz. We notice it's much higher in frequency than the 100 hertz. So we want to allow the 100 hertz to pass through the filter, and we want to reject or reduce this 30 kilohertz tone that's also trying to pass through the amplifier. You find that in audio system when you have some kind of buzzing or some kind of high frequency noise in the system, we put in filters to remove them. So design a filter that basically, and this is basically what that problem 3 in your homework assignment is. Design a low pass filter that passes the desired signal and then rejects the noise waveform. So pretty much this is your schematic that you'll be using the capacitor and the resistor in parallel, the negative feedback to the inverting input, and of course you'll add your power supply. And when we put this icon on the schematic page, we may have to flip it to make sure we're using the inverting terminal as the input to the circuit. So your procedure in a homework assignment is to find the source resistor, find a feedback resistor RF, and then find a capacitor feedback. So it's 3 parts to the paper design. So to start the paper design, you're going to be dealing with what we call Bode plots, and these are frequency or bandwidth plots of the circuit. And at the bottom here, just kind of briefly cover what this kind of plot is. And let's see if we can give an example of one. So we're actually going to go through the design of this particular low pass filter, and we're going to set up this is an AC sweep. So I'm setting up the AC sweep here, and as I said, we'll go into design. So we're going to sweep from 10 hertz to 1 megahertz, 1e to the 6 in a log sweep, and then maybe 300 points per decade. And then we'll run the simulation. So in the plot window that comes up, we're going to add a trace. And Bode plots are in decibels, so we'll need to click on dB parentheses over here. Once we click on that, we go back over, and then we'll plot the output voltage, V out. You know that V out is in the parentheses here, and then we'll click OK. So this is a of that low-pass filter. Over here on the y-axis, this is in decibels: 0, minus 10, minus 20, minus 30, minus 40. And then the lower on the x-axis, this is frequency from 10 hertz to 1 megahertz right there. So the Bode plot at low frequencies, this circuit has 0 dB gain, which is a gain of 1. And as you go higher in frequency, the output is dropping in decibels. And it's dropping very quickly. So this is what the Bode plot is doing. And so we can put something on here, and then at the bottom here, move this over here where it's flat. And this is called the pass band of the Bode plot. And you notice down here it's saying something like milli or micro. That means it's basically equal to 0. And then we'll move this to where till it gets to minus 3 decibels. So we're watching this term here. So that's at minus 3. And we'll click on a marker. So this is called the minus 3 dB frequency of the Bode plot. So this minus 3 dB is 496 hertz, and it's minus 3 dB down. This is called the crossover, or it's called the breakpoint, and it's also called the minus 3 dB point. So in our, what we basically have here, so this example plot here, this is a kind of a simplified Bode plot. It's showing here 0 dB frequencies pass through, and then once we get through the cutoff of minus 3 dB, the output of the plot begins to drop. So to design this amplifier, the first frequency, 100 hertz, we want to put it in a pass band. So it passes through with a gain of 1. However, the 30 kilohertz, which is F2, we want to put it somewhere on where the output of the filter is dropping. Out here maybe somewhere. So to do that, again, here's a version of the Bode plot similar to the P-Spice. So we want to put the 100 hertz somewhere, anywhere in this, according to the frequency where it's about 0 dB gain, and then once we pass through the cutoff frequency minus 3 dB, the 30 kilohertz will be out here somewhere. Well, maybe minus 20, minus 30, or minus 40 dB gain. So it will be greatly reduced when it gets to the 30 kilohertz frequency. So your challenge in your homework assignment is going to be, because your filter's corner frequency is the last 4 digits of your Z number. So what you'll do is you'll take those numbers, let's say they're 1, 2, 3, 4, and your cutoff will be from that number. Those first, and that's in the hertz. So since it's 4 digits, assuming if there are no zeros in there, or if the first number is a 0, you're going to be less than a kilohertz. If the first number is, if your first number in your last 4 digits is 9, what's your frequency to start with? 9,000. And whatever comes after that, if your first number is 4, that's 4,000. So 4 kilohertz, and then whatever 3 numbers come after that. So you'll design with that frequency, and now you basically have to design a calculate RF and C sub F. So the cutoff now is where we want the minus 3 dB point to be at. So your cutoff now, we're going to go back and change that slightly. Your cutoff is going to be above your calculated frequency, which is Z number. So F1 is going to actually be the last four digits of the Z number. That's going to be your desired frequency to pass through the filter, and then you're going to have a cutoff frequency that you just select, and you basically want the cutoff to be the minus 3 dB. And you don't want it to be too close to F1, the four numbers in the Z number. You don't want it to be too close to that, or it's actually going to reduce that. Now the other part of it is that the higher frequency, let's say it's 30 kilohertz, you want that to be attenuated as soon as you pass through this minus 3 dB breakpoint here. So you have two requirements. Your cutoff should be away from your desired frequency to pass through, and then it also should be far enough away from the interfering frequency such that the 30 kilohertz can get pretty far down. So if we go back to this simulation curve here, if an undesired frequency, let's say is 30 kilohertz, and that's about right there. There's an undesired frequency. 30 kilohertz, it's minus 35 dB, and we'll assume the desired frequency and we might have to change the scale slightly. Just move the scale up slightly, and then we'll put a marker in for the desired frequency here, which will be the 100 hertz. So there are three frequencies here in this design. The desired frequency is 100 hertz, which is here, 98 is pretty close to 100. The undesired is 30 kilohertz here, and then the cutoff, minus 3 dB, is 490, is around 500 hertz. So this designer, the last four digits of the Z number was 100. And that turns out that's the frequency they want to have pass through the amplifier. And the interfering signal is 30 kilohertz, so the designer had to choose a cutoff frequency. So here it's decided let the cutoff be 500 hertz. So you notice 500 hertz is far enough away from 100 hertz, so it doesn't reduce to 100 hertz. And 500 hertz is also at a point where it helps to reduce the interfering signal, which is 30 kilohertz. So you'll, depending on your last one number of the Z number, you'll be ready to calculate, to kind of guesstimate a cutoff frequency.
So it's important to have that gap.
You want to have that gap in here. If the cutoff is too close to your desired, you're going to reduce your desire. If it's too far away from the interferer, then the interferer will move back up and be present in the system. So, and which means it's arbitrary. There's hundreds of ways to actually meet that specification. So the designer here, let's say, chooses a cutoff of 300 hertz compared to the desired frequency of 100 hertz. So without using PSpice, we can calculate the gain of the low-pass filter at 100 hertz. So we go back to the equation. This is the equation for the passive low-pass filter. And now we change over from the S domain to J omega, and we calculate this equation here. This is the gain of the low-pass filter at 100 hertz. So 1 over square root of 1 plus F1 over Fc, square that, and that's approximately 0.95, which is approximately 1. If you wanted this to be 500 hertz cutoff, you just put 500 hertz here, and then you can predict how much of the desired you're going to attenuate. That's pretty close to 1. And now at the same time, we can change F2 to 30 kilohertz and calculate the gain at 30 kilohertz. And that's 0.01, so you can calculate 20 log of 0.01. What is that on your calculator? Log 10 of 0.01. You're going to get a negative number, but that's okay.
You're going to get negative 2?
20 times log 10 of 0.01. Now it's got to be a number much smaller than 0.95. And it's going to be negative. Now 20 log of 0.95 is approximately 1. So 20 log of 0.01 is going to be a large negative. And it's converting it to decimal.
20 log of 0.01, correct?
Yes.
It's negative 40.
So this is minus 40 dB here. That's minus 40 decibels. And this is approximately 0 dB up here. So that's a reasonable attenuation to expect from the system. 40 dB attenuation of the interfering signal. And at the bottom, the lower part here, this is predicting what PSpice should produce if we actually design this filter. So you're going to have PSpice 5 times the real amplitude times 0.95. This is F1. And then F2 is going to be 5 times 0.01 here. And then trigonometrically, we combine both of these. They're both sine functions. So we can combine those, and what should come out of PSpice is 4.75 sine of 2 pi 100t. So what's missing is the 30 kilohertz here. So this is assuming a very ideal filter that's going to completely remove the 30 kilohertz interfering signal. assuming as we say, it's an ideal filter, so there won't be any 30 kilohertz in the system. So with that, the designer, let's say, decides the cutoff will be 300 hertz. Now the resistors, the capacitors, you can pick the resistors or pick the capacitors. So again, because there are hundreds and hundreds of combinations, let's say we decide capacitor is 0.1 microfarad, you might decide 0.5 microfarad or 0.8 microfarad or 10 microfarad. It's your decision. So we take that, put that in a formula for the cutoff, and calculate resistance 5.3 k ohm. So what's the cutoff? What's the equation for the cutoff frequency? 1 over 2 pi r of CF. So we pick CF to be 0.1 times 10 to the minus 6. The cutoff is 300 hertz, and then we solve for this resistor R sub I. And you basically complete it. So here's the 5.3 kilohertz, K ohm, here's the 0.1 microfarad. We set the feedback resistance equal to the resistor here. And this is a version from P-Splash, so we can go back to, so that board problem, it requires at least two simulation plots. So this first plot, this is the AC Bode plot. We'll go back and change these to 5.3. And again, we put in dB for AC, pick dB, and then V of V out. It's actually V out over Vn, however Vn is equal to 1, so you can leave that off. And so there's the plot. So once you get the plot, probably will widen the plot slightly. And again, now we go back and we'll check to find out if the 3dB is anywhere near the cutoff. At the bottom here is minus 3.01, and we'll put a marker on it. So there's 300 hertz minus 3 dB that meets the design spec, and you probably need to change your y-axis so that the marker will still be visible. I'm going to change this to maybe instead of 0, change it to plus 10. All that does is just moves it down, and now you need to put in another marker, and this is at the 100 hertz. So there's a second marker, and then a third marker at 30 kilohertz. probably go in and change the font size so it's more obvious. And similar to predicted, right around 30K is 30K is around 40 dB minus 39.7, and at 100 hertz, it's close to 0 dB, close to 1, and the cutoff is 300. So your cutoff frequency on your PSpice AC plot will resemble this for your homework 3 problem. Now you also so that's the first part you'll need for that homework assignment. And now it says to do a transient simulation also. So you'll go back in and find a V-sign generator. So you'll have two schematics, one for AC and one for transient. So this is for the transient. Now, hopefully you're taking some notes here because we're actually pretty much solving doing a PSpice simulation for your homework problem 3. So you'll have this first generator will set the offset to 0 DC. This one didn't have an offset. The amplitude is 5 volts. The frequency is 100 hertz. This is the desired. And then we'll just set this AC parameter to 1. You can also do an AC sweep with this source also, with this AC parameter. Now, you need to add the 30 kilohertz interfering waveform. And the way we'll do that, we'll move this wire, we'll click on this, do a Control C, and then a Control V. We're going to add a second generator in series with the first one. And then we'll add the wire connected. And then our ground wire. And you can set this offset to 0. The amplitude is 5 volts. And what's this interfering frequency? 30 kilo. We'll set this to 30K. So we have two sources on the input for transient for both 5 volt amplitude. And now our simulation profile, you'll change that to transient. And the 100 hertz, if we want 5 cycles of 100 hertz, how long should the simulation run for? We want 5 cycles of 100 hertz. How long should the simulation run? What's the period for one period for 100 hertz?
10 milliseconds.
10 milliseconds. So, well, it's not going to do anything to the simulator except it will run a long time if we offset. So we'll say 50 milliseconds, and we'll set the step size at 10 microseconds. save in case the server changes. Now this time, when you transit, you do not use the DB function. You just plot the out. Is that correct? So the question, once you complete your paper design, that's 50%, the other 50% is piece price, and then explaining, is it actually working the way it's designed?
Yes.
Now, again, this is not the same as the homework assignment. However, the prediction from this assignment is that the 30 kilohertz will be removed. That's basically the idea. And according to your calculations here, at the bottom, according to the calculations that you'll do in your assignment, the output should be 4.75 sine of 2 pi 100t, and we'll just say the deal. So the amplitude from piece price should be 4.75 t, and it should be 100 hertz. And again, you might have to raise that slightly. And then next you'll put a marker on it. And put a marker on the mid. It's not necessary to put one on, you can put one on the minimum too. You'll find that depth is going to help in grading to make your markers larger, because then you won't have points take them off because it's not readable. So what's the peak-to-peak amplitude of this waveform approximately?
9.5?
4.75 minus. So it's approximately 5. However, in your write-up for your homework assignment, if this were actually a problem, you would be confirming that your paper calculation of 4.75 is correct. Now the other part is it actually removing the 30 kilohertz? So to do that on the schematic, you want to plot Vn. The Vn is 5 volts amplitude, so it's a large waveform. Add Vn. Now, is that okay?
No.
We'll look at this version of it. So this version is saying that Vn goes plus 10 to minus 10. And the reason it appears that way is because the scale was changed on the y-axis. So if this happens, What should the scale be?
10.
Negative.
So that's minus 10 to, so the input waveforms are 5 and 5. And this is what you're reasoning, because you don't just accept piecewise numbers. You're basically reasoning whether this is actually correct. So if the input waveforms are 5 volts and 5 volts, when they add together as a summary, the amplitude is going to change to 10 volts. So this is correct. The input is going from 10 to minus 10. What's in this larger waveform?
It's a bunch of smaller waveforms.
The larger one.
It-
30.
And why does it appear like that?
Extensor.
That's the mix. The signals are mixing on the input to the amplifier. The 100 hertz is here, and the 30 kilohertz is there also. So basically, when they add algebraically, this is the way the waveform appears on the input. So the waveform is correct. You get a wave kind of a fuzzy waveform on the input, and then you'll just have to make maybe comment. Now this version here, when it was printed, it's not in color, so you notice the way to actually, the better way to do it then is to add a second plot. And this will avoid the plotter changing this, not being so happy with the scales. So you put VN on a separate plot and then remove it from this first plot. And now you'll have something that looks similar to this right here. So it's showing that the filter is removing this 30 kilohertz noise and only the 100 hertz is passing through the filter. So this basically is going back to, this is one with the 500 hertz. So this is a different filter, and make sure you practice these in your, as homework assignments. It'll definitely be prepared to do the actual assignment. And here's an earlier midterm question about a low-pass filter. Says we need to remove a 50 kilohertz AC signal of amplitude 0.5 volts from a desired 1 kilohertz AC signal of amplitude 5 volts. And that's the only information that's given. So design the filter. The schematic is not given. So you need to memorize the schematic for a low-pass filter. Here's the schematic. The way this is drawn, it's a 50 kilohertz input and a 1 kilohertz. Up here, the desired signal is 1 kilohertz. So what is the cutoff they picked here?
2 kilohertz.
It's actually 2 kilohertz. It's kind of an error. It says 5. So 2 kilohertz is close to 1 kilohertz. It's also far away from 50 kilohertz. So picking that and pick a capacitor. This side is 0.1 microfarad. Solve for the resistor, 796 ohm, and then set RS equal to RF. The gain is equal to minus 1. And the design here is complete. And then this version, this is similar to your homework assignment. So let the desired signal be AC with amplitude 3.2 volts and frequency. The last 4 numeric numbers of your Z number. What's your frequency? The noise is 2 volts with a frequency of 30 decide on your cutoff frequency. It can be 1.5 to 2 times larger than your desired frequency. Use two 15-volt batteries and calculate the attenuation of the 30 kilohertz noise and compare this with the 30 kilohertz attenuation revealed by your AC sweep. Everyone follows what this is asking for. Is this actually in the homework assignment? Yes. Calculate the attenuation of 30 kilohertz noise. Compare this with the 30 kilohertz attenuation revealed by your AC sweep. And an example that we went over here this was the calculation for this filter, and it was that when you get to 30 kilohertz, it's going to be minus 40 dB difference. So this is the second part of the homework assignment. And differential amplifiers, another op-amp application here. And differential amplifiers can behave as filters even though they do not have capacitors in them. So design an amplifier that will amplify any desired signal while rejecting any undesired signal. And what is that? How is that different from a low-pass filter?
You're amplifying the original signal, not just removing the noise.
It will. Well, this word "any" in what you're saying, the low-pass filter, it will only reject the frequency that you designed it to reject. This particular amplifier will reject any undesired signal. So it's like having a million low-pass filters for any frequency that tries to pass through it. And that's very unusual for a circuit to have that capability. And at the same time, it's saying that if there's a very small input signal and there's a very large undesired signal, there's one here, there's another one here, it will reject all of these large signals and only allow the small signal to pass through. And that's very different behavior from a low-pass filter. The low-pass filter is tuned for certain frequencies. So let's say that the undesired signals are called common mode. Yes,
Is this a bandpass filter?
there are no capacitors. You already have a filter, but you got a capacitor on a coil inductor. So this circuit is only using resistors. So the undesired will be common mode signals, and the desired and the common mode appear simultaneously at the input to this amplifier. So basically it appears simultaneously. You consider filtering the common mode. So the first design attempt is to design an active low-pass filter. And we did that. Let's say the common mode is 30 kilohertz. And then suddenly the common mode changes to 8 kilohertz. Now you've got to go back in redesign the filter, and the common mode changes it again to 60 hertz, now you have to change it again. So common mode interference can be considered random and difficult to remove by filtering. And that's because it keeps changing frequency. And once you design a low-pass filter, you have to keep redesigning it and try to track the common mode. So what we want here is a circuit that will behave the same at all frequencies in terms of rejecting if they're not supposed to pass through there. So common mode interference can have amplitudes much greater than the desired signal. So the room we're in, what's a large common mode signal in this room? When you go back to your residence, it's waiting there for you.
Computer?
Wi-Fi?
The lights. The 60 hertz common mode from the lights in here is it's very high level. And it's electromagnetic waves, so it's not visible, but it basically is on it's everywhere, and on everything. And if you go outside, you still have common mode because of all the cellular and all of the communication waveforms that are there. But in here, 60 hertz is a very large common mode signal, electromagnetic wave. So if you wanted to reject 60 hertz, then this circuit has to be capable of rejecting it, even though it's very large, several large voltages. So, and it can be random. This is a method of, it usually works with common mode signals, and that's the ground here. And that's actually earth ground here. So if we have a relatively good earth ground, we can short circuit signals to ground. But finding a good earth ground is not that simple to do. And then if the signal, so this only works for low frequency signals. So this is a circuit, and it's what's missing from this circuit? Ground is missing. So whatever is circulating here, it has no path to escape unless you actually ground the circuit. So this is a floating noise signal. So here's another random noise, basically appears, and it says white noise or green noise, different types of noise signals. How do you reject these? How many frequencies are in this noise?
Yeah, there's a lot, many.
A lot of frequencies right now. And so a low-pass filter would have lots of issues trying to reject random noise like that, especially high level. Now, this is if we were to investigate a 741 op amp